We want to look at restorative buildings where we can bring energy and water treatment to buildings around. So that's where you start hearing about eco-districts. PSU has an eco-district that's in the early planning phases that I've been to a few meetings on. There's actually a proposal out right now for the South Waterfront eco-district that's PDC is involved in. So kind of a status of the industry. But this presentation, I wanted to talk about what steps we've taken. So a little bit of past, and actually, you know, this building is kind of a past. It's in the steps, but it's certainly been superseded by some other designs and some other things that are making their way into the more mainstream. So I'll get going with this presentation. Just a little bit about PAE. We're a 43-year-old company that's based in Portland, Oregon, and we've just opened an office in San Francisco. We serve pretty much West Coast region, including Hawaii too. It's off the side there, but Hawaii is actually a great environment when we get a chance to work there because they have 30 cents kilowatt hour rates for electricity. So the stuff that we struggle with here to find payment, over there, everything's low-hanging fruit. So it's very interesting. I'm doing a project in Hawaii right now. These are the type of sectors we cover. We cover all sorts of types of buildings within the building industry, built environment. So we get exposure, and we get to cross-pollinate quite a bit too. You know, if there's a type of design or type of system that works well in one building and we see the ability to transform that design into another sector, it can be very enlightening and very forward-moving for some of these, like a medical sector, to take what's being done in an educational sector building. And it helps them move forward in things that maybe they weren't, you know, the designers who normally work on those type of buildings wouldn't think of that. So design approaches. This is an approach that we like to advocate for in all of our building projects. And one of the very last things you see down here is renewables, because really conservation is the big key to bringing and delivering these buildings, water and energy conservation. So setting goals and reducing use and designing efficient systems is really the first steps that you have to do to bring the system scale within the project, and almost more challengingly, the budget. You'll hear a lot of information about what do green buildings cost, what does sustainable building cost, what's a platinum building cost. I'm not going to give you an answer because all answers are different. It really depends on where you start from, and it depends on your owner and what kind of journey and path they want to go on as far as trade-offs within a building. But it's really a step right now that people want to think that it's less expensive, but you've really got to work with your owner to get the ability to trade off either for thermal comfort or for lighting or for acoustics. Sometimes in educational sectors, you know, we get very challenged with acoustics, where we would like to give up the carpet and take the thermal mass of the floor and include it in the room, but a lot of times they won't allow that because they really value the acoustics of the space. So many different things to do. I'm not going to dwell on this. I really want to get to talking the stories. And so here's a building that you all know, the building we're in right now. This was a building that we designed, and it has some features that are on that path to net zero. One of the features, geothermal system. It has gains its heating and cooling energy from an open loop that's actually, the wellheads are located within the basement of the fourth floor, or the 4th Avenue building, which is right next door. One of those wells was existing when this building was built, and so there were 2 wells that were added, one reinjection well and one well that draws water out of the aquifers. There's actually 2 aquifers under this building. We draw water out of one and we reject the water into another one within the substructure. I think one's at 600 and others at 800 feet below where we're at now. So very interesting how that works. There's basically chillers that are heat recovery chillers that bring the heating cooling energy into the building. And this is a design, a geothermal design, an open or closed loop geothermal design is something that is definitely on the path to net zero type buildings. I'll show you another buildings when we go forward. This building has a little bit of a natural ventilation within the atrium space. There's operability within the windows. That's another piece that is very important to enhancing the operations. is to take advantage of the environment. There's a rainwater system in this building. At the time this was put in, this was one of the more of the forefront of rainwater reclamation systems. Rainwater reclamation systems have now kind of graduated to kind of like commonplace in our industry and in our vernacular of clients and building owners that we work with. It's kind of like, oh, yeah, rainwater, great, it's good. You know, everything's kind of known. The systems are pretty prescriptive. The codes are very prescriptive for using the water now. So it's an industry, or it's a system, I guess, that has shown that you know, with acceptance and with use, it can kind of move over into the commonplace. I was mentioning before we started here, it's like the lighting in most buildings now that we're designing have addressable ballast. So there's no questions about dimming because the ballasts sit on a network and you can program each and every light to do whatever you want it to do whenever you want it to do it. So you can create endless scenes for lighting and create energy conservation in the way that best suits the use of the room and the space. So that's, you know, there's many different things that are progressing. That's another one that's kind of now at the more commonplace, where whether the ballast is being used for dimming or not, most light fixtures that you buy come with a dimmable, addressable ballast. This is the heat exchangers in this building that do the transfer of energy from the geothermal open loop system into the heating and cooling loops that are controlled from scroll compressor chillers within the building. There's a 200 and a 400 ton machine in the building. Most of the time this building runs on the 200 ton machine. It's well within the parameters, only when the outside temperature, I think the operator that I met with said, you know, high 80s is when they actually have to bring the larger chiller online. So the building's actually been operating quite nicely. The 45 EUI is important to note. Do you guys all know about EUIs? It's kind of like the measuring stick that we use for the energy in the buildings. kBTUs per square foot per year. And these are numbers that we can get very easily from utility grade bills. And so some of these projects I'll show you have, you know, studied. This was a studied EUI, but we actually have actual data because we're now putting in measurement and verification systems in a lot of the buildings to study the use and to get that feedback. But an EUI is simple because you can just take the utility grade bills and get it. Another building you know, thought I'd give you some easy ones up front, some ones that you may recognize. Shattuck Hall. Shattuck was an interesting project in that it was a conversion of an old, I'm not sure if it's historic, but it's definitely in the age that it would be considered historic. But this building was interesting because it explored the use of radiant heating and cooling. And it did it in a scale that, or in a scale maybe is a good word, but it did it in a way that was easily integrated into the classrooms and into the building systems. This building is served from the central utility plant that has kind of a distributed energy approach for the campus. And there's like campus chill water. I know there's chillers like over in the old Science 2 building that are part of that loop. But this is one of the buildings that's served from that loop. And so the chill water in this building and the heating water go into the radiant panels. One of the things that was done is this building used to have like a multi-zone type of HVAC system, which is very inefficient. A lot of simultaneous heating and cooling with multi-zones. But what we were able to do is we were able to take that infrastructure and turn it into a dedicated outside air system. So very economical to take ducts that go to every classroom and convert them from mixed air to outside air. And they were much larger than they needed to be, so the pressure drop was very low. Ended up being a great thing for the building. Very efficient. Systems are already in place. All we had to do is take out the old air handler and put in a new dedicated outside air handler in that space. And then the radiant panels, you can see them here within the space. They're off of these closets that are adjacent to the room. And there's one off the photo right here. The closets have the valving that change over the panels from heating to cooling. And so it's actually been very well received. This project was being designed at the same time as the Port of Portland project that I'll show you. So we kind of collaborated efforts together in the office as far as evaluating radiant panel manufacturers, looking at different styles of panels, looking at the trade-off for economy and performance of panels, We looked at radiant sails, we looked at chilled beams, we looked at all the different type of elements that can go into a space. Radiant sails and chilled beams are great for cooling and where you have a high cooling application, but not as efficient for heating. And our climate is more skewed for spaces, you know, depending on their use, it's more skewed for heating. So it was a nice effect to use that. We also use ceiling fans in this design, which introduces a little bit more range of space ambient temperature to for your mean radiant temperatures in the space to have more variation. So we were talking before this, it's like there needs to be the industry doesn't have a sensor system that can accurately communicate with the occupants what the effect of these systems on their bodies are. Because we all know that, you know, a temperature sensor in the space is just measuring air temperature, but with a radiant element and an element that's putting air over your body with a evaporative effect of your skin, there can be as much as 3 or 4 degrees difference between what your mean radiant temperature is and what the space ambient dry bulb temperature for the space. So, but there's no system in place really right now to know that as far as what that is. It's individually calculatable, but in a scale of a building like this or other buildings, it's not something that is quite frankly done as far as calculating every zone's percentage of mean radiant deviation from dry bulb. So there's interesting things there to study more. But this design was a first generation of ceiling radiant panels that were 2-pipe changeover. So every one of these rails sits on the panel, and these are the pipes that contain the fluid, and the fluid's all controlled from either a control valve or a pump that for every zone, and so it changes the panels from heating to cooling depending on what the space needs. This is a project that I know really well. I lived with this project for about 7 years, from very start of conceptual planning to delivery of a space that's been operating for almost 2 years now. This is the Port of Portland headquarters out at the Portland Airport. The building itself has 7 stories of parking with 3 layers. You can see 2 of the layers here of office. There's another layer of office on top that's slightly set back. This is the north wall. This project was a really good example of an integrated design process. You'll hear, I don't know if do you hear like one of the industry buzzwords right now is integrated design, but there's really no common definition for what that is. But in my world, integrated design means we make changes to like an architectural system that actually has benefits to the mechanical electrical systems of the building. You look more holistically at the building as a whole. And in this building, you see this north face is a triple plane glazing system. It's a storefront system. Benson Industries, local manufacturer, put this together. The outer 2 layers are laminated, and it's mainly for acoustics because they're next to the airfield, and there was a thought that the airfield ambient noise is quite loud, and the office workers wanted to be in a little quieter environment. But it is also an enhancement as the north side of the building is closer to the airfield than the south side of the building for thermal performance. So it was kind of a double edge there that we got from acoustics and thermal. But it's interesting is as you see these, the building has a very unique design, but these solid elements are spandrel panels. Those spandrel panels were driven by the engineer. The engineer, me, said, that wall is taking up too much energy for heating and cooling. Even though it's a north wall, it has a slight orientation to the east, so you do get some direct sunlight on the wall at certain times of the year. So I said, well, why don't we get some spandrel panels and start reducing the actual glazing area on this wall, but yet still keep the floor-to-ceiling glass that everybody loves to, when you stand in the space, it's quite dramatic to have a floor-to-ceiling glass assembly that you're looking out into the outside environment. So we drove actually these vertical elements, and it got rid of all of the exterior heating zone on the north side of the building. So we gave all that money back to pay for that glazing system by taking what would normally have been some type of in this application, maybe a fin tube or increased radiant panels at that edge, and we gave that back to the system or the project as a credit because we introduced these solid elements, and they still got the feeling of the building they wanted. So that's a really interesting way to think about integrated design. This project also has a on-site wastewater treatment system known as a living machine. Treats all of the black water for the building, turns it back into gray water, and puts it back into the flush fixture. So it's an enclosed loop. The geothermal system for this project is wells under the building. Oh, I won't go to that now. The wells under the building are closed loop wells, where this building is an open loop well where we're drawing water from an aquifer and we're re-injecting to another aquifer. This building, it's a closed loop piece of pipe, and it's acting just like a very, very large heat exchanger. There's 200 wells. They're 340 feet deep. They reach down into the ground below the parking structure, and it's like a giant energy heat sink source, either rejecting heat or pulling heat from the ground. That's the other type of geothermal system you'll hear about. And not talking about like Klamath Falls geothermal, where that's the, people would consider that like more of a hot geothermal, and they, more of a cogen type operation off of that, or a heat recovery. So geothermal is another one of those words like integrated design that in the industry right now is kind of finding its definition, finding which applications best fit. So it's kind of confusing in some ways. South side of the building, this is south side of the office structure. These are the 3 floors of the office. Like any south side of the building, it takes a tremendous load. So you can see all the various shading elements. There's a large shading canopy at the top. There's deep inset windows. There's light shelves here. There's actually a blind system behind the windows that has a automated solar sensing device on the roof that knows the time of day, knows the azimuth of the sun, and takes in the intensity of the sun, and then automatically pitches these blinds to provide the right amount of shading and the ability to bounce the light up for intrusion of daylighting. So lots of systems went into the building, but again, like the north side of the building, this south side, we made all these changes, and what we got rid of was supplemental cooling zones on the south, because we made enough change that we could actually look at the interior environments inside and justify that we didn't need those exterior zones. So that simplified the mechanical system, but it takes a lot of work of working with the engineer, with the architect, to bring that into effect. This is an idea of what the space inside looks like. This project also has radiant ceiling panels, dedicated outside air system that's above. This is an open office environment. This is a project that the port was moving from a more traditional enclosed office environment into an open office. The CEO has an open office. The only offices that are in the building are for the legal staff, because they couldn't convince the lawyers to get out of their offices, but they tried really hard. They couldn't get the lawyers out. So there's 6 offices that are dedicated towards the port legal staff, but everybody else is open environment, low landscape partitions, daylighting and views. This is that curtain wall system to the north, so you can see the floor-to-ceiling glass. And everybody in the space that works back here has that view, so it's a very good environment. They're getting a lot of their conditioning from the radiant panels. I was out there on a 28-degree day, and the radiant panel was measuring 75 degrees. It was barely heating. So the system runs great. The occupants, there was a occupant survey that was done as a study here in the university that's actually produced a report of what the satisfaction now after 2 years of operation is for the space. So this UI 42 is an actual. So if you look at it, that's it's a path to net zero, but it's not net zero. Net zero buildings that are producing their own energy need to be in the below 20 range. So this building did a lot of optimization to the skin, optimization of the delivery system for the heating and cooling to the space, but still, on a path to net zero, fell short. On the water side, this is the treatment plant. It's in the lobby of the building. If you have a chance, stop by. It's open to the public. You can walk through. Doesn't smell. The water's always like 18 inches below the planning grade. And it goes through a primary settling tank first before it goes into this treatment operation. And these are treatment tanks on the outside, and these are treatment tanks on the inside, and it's a batch flow system. It's called a tidal wetlands bed system. Worrell Water Technologies is a company that's currently licensed for living machine application. Basically, in the world of on-site waste treatment, there's membrane bioreactor, which is a very mechanical process. That's OHSU health and healing building down at the foot of the tram, or there's this, which is a more passive approach with just basically batching water from tank to tank and letting the enzymes and the biological components happen within a tank basis here to provide the clarification and the removal of the nutrients in the water. So those are the two main systems that are in play for buildings right now. Eco-districts are considering living machine type applications because they're fairly compact. This system, it was designed to treat 5,000 gallons per day. It's currently treating about 3,000 gallons. So it's a little under capacity right now, but we have some reserve capacity that we're planning if there's more systems in the future that want to be sourced for this. So, you know, it's scalable, but it's, you know, it's also something we're working with their neighbors next door. A lot of the cost associated with these systems has to be traded off with system development charges. When every building is built, there's a system development charge that goes in for waste fixture units that are going into a building. And for this building, an example, the system development charges were about $700,000 for the city, well, for the Port of Portland to pay the city of Portland to bring those plumbing fixture units online. This system is about $1 million total development cost. So there is some trade-off. The Port, very conservative client, has a full line bypass, so they not only paid the $700,000 system development charges, they also paid the $1 million to have the system put in. But they wanted to be a little conservative as far as providing that the system was not, in their eyes, not exactly proven yet. But it's been in operation for 2 years. It's never had a time where it's failed to operate. But there's been a lot of exploration and learning during this process as far as getting this type of system running. But this is very important for net zero water, is to have on-site waste treatment. This is a graphic that shows those wells that are under the building. It kind of gives you an idea of the scale and the reach of what that heat exchanger is doing under the space. It's a high-density polyethylene piping. That's the same piping that Northwest Natural uses for running high-pressure gas lines through the city of Portland. It's very resilient. You can freeze it up solid. You can move it, deform it. It's a very good material for use in underground, because once this goes in, the procedure is that you drill like a water well. You drill a well with an auger bit. You pull the auger bit out, and you have this 5-inch diameter hole that's 340 feet deep, and then you bring the piping material. This is some pictures of that happening. It's a very dirty process, actually. They grout it with a cementatious grout that provides the thermal conductivity from the pipe to the soil and actually kind of locks everything in place. So it's kind of like a slurry. And this is the pipe itself as it goes down. This is the very bottom. They usually attach like just a crude weight to it, and they stuff it down. And so as they stuff it down, they get it to the bottom, and then they take what they call a trimmy pipe, and they slurry from the bottom up to seal the hole. But once it's in there, you're not getting it back out. You're not pulling it out. And in this application, it's over the top of a 7-story parking structure, so you're never going to get at it. But this project, we have subsurface tunnels that are in for pedestrian. If you've ever been, you know, like in the tunnels out there, they have the pedestrian tunnels that run under there. So one of the tunnels has a utility tunnel that's next to it, where we take all of those wellheads into the building, and then we have control of making that interface between the piping that was put in for the ground system and the mechanical system in this building. The system in this building, it consists of the wells out here. There's a small cooling tower that's actually only a 50-ton cooling tower. It's like a little peaker plant to take the hottest days. But it actually hasn't been used that much because the ground field is actually working quite well. We have modular heat recovery chillers that produce their production of the heating side is up to about 140 degrees, and the cooling side, we're only bringing it down to like 38 degrees, but they can go far below freezing. So these are rotary scroll compressors that you would normally see like on just a packaged rooftop unit. So It's a very simple process with some plate and frame heat exchangers and some scroll compressors up here that actually produce the heating cooling energy. We take it through heat exchangers because the port really didn't want to take any undue risk with bringing waters that we considered that possibly if there needed to be more capacity in the future, we could run a glycol loop, or we could run a glycol solution in part of this loop. So they didn't want to have glycol up in the office space from a hazardous material standpoint. So, and also there's a height difference. This building, think about it, it's 340 feet down and it's 10 stories up. So there was some concern about reaching the maximum pressure at the bottom of the well with the material for the piping. So this is the way that it sets up in the cooling source, where we're basically rejecting heat into the ground. And then conversely, when we're taking heat out of the ground, we're basically just taking chill water out of the evaporator side of the chiller and pumping it into the ground and getting heat out of the ground and then bringing that up into the building. The building includes a 2,500 square foot data center that services the entire port's aviation and marine operations. So we kind of have this great heat source that's running all the time within the building. So a lot of times we'll run on a group of maybe 5 to 8 wells, and it'll carry the entire building. The building's 225,000 square feet. So it can work very efficiently in a day like today, where it's very moderate temperatures and no extreme loads. This project is it's up in Olympia, Washington. This was very interesting because this was an example of how you can work with an agency and their process. This is a waste treatment plant. And so what was done on this project is part of that process used to be that they would take the methane gas and they would run it through a boiler, and they would fuel the boiler with the methane gas and turn that heat back into their digestion process, part of the waste treatment process. And then what excess methane gas they had, they would just simply flare it. So this project took that process and changed pieces out of it. We actually put, and this is the location, it serves a Lacey, Olympia, Tumwater, and Thurston County, so it's kind of like a regional center for waste treatment. And this is the site that it's located on. The building itself is actually, the administration building is right here. And an interesting story, there's a children's museum that's in construction, or nearing the end of construction, I think right now. That's actually, its energy is the heating energy and cooling energy for that building is sourced from the system that we created over here. So it's actually, we're giving back to in a restorative nature, we're giving back to other buildings in the surrounding area. So this is the way the system works. It used to be that this was the location for the boiler. We'd take the methane right through the boiler and it would go into a high temp loop and that would feed back into the digester. So we took that out and we put a cogeneration plant, basically a engine-driven generator there. And we take the waste heat from the generator and we run that through the high temp loop to do the process that it needs to do with the digester. But then we also share that heat with a lower temp loop, which actually acts like a condenser water for our building. And it serves the heat pumps in the space. So we can either extract heat for the building or we can reject cooling by taking the process here has a large amount of effluent water that they treat and then they put back in the bay. So before it goes back in the bay, we run it through the heat exchanger and get rid of the heat from the systems in the building here and from the high temp loop here and put it back into the bay. So this is a good example of like a energy recovery cogen operation where you go into these plants that have this capacity. And a lot of the system was already built by the time we got there. But we just made some changes here with the cogen feature and here with the low temp loop. And so then the Children's Museum just connects on to the low temp loop and comes over here and receives its energy as well at the same time. So it was a great way to save a lot of energy and take advantage of a process that was already happening over here. But again, EUI at 38 for the building. We're not down to net zero yet. So, but we're exploring these processes of saving energy with conservation within the building, but we're also finding alternate sources to get the energy. So these are some outside shots. This building, I was showing you on the port building, they had the internal blinds. This building has external blinds that are operable on the south side. So a lot of the, controlling of the space envelope really can be quite beneficial with exterior shading that's operable, because at times like wintertime, low sun azimuth, you want that sun energy to come in from a daylighting aspect, and you can frankly withstand a little bit of the energy penalty of taking that heat into the building because you need heat. But in the summertime, I mean, you want to shade it. So it really works well to have these systems, but they're just not quite well developed for the United States yet. They're still quite expensive. There's like airport in Munich that has a whole wing of the airport that has large 6-inch blades that controls east and west exposures. So I mean, there's large applications. It just hasn't made its way here yet. This is another look at the building. It created this great kind of almost community center out of a waste treatment plant. How did this get in here again? I had this problem. I'm sorry. I was going through this presentation this morning. I found a couple doubled up slides. Okay, so this project. How are we doing for time? We're doing good? Yeah, we're doing good. This will be the last project I talk about. This is a project that is in construction in Seattle. This is the Holy Grail. This is a building that is net zero energy, net zero water. This is the Bullitt Foundation in Seattle is sponsoring this building. The actual name of it is Cascadia Center for Design and Construction, CCSDC. Everything's acronyms in our world. It's so painful. So this building is a very interesting story because very motivated owner, Dennis Hayes, Bullitt Foundation, one of the co-founding creators of Cascadia Chapter, USB Green Building Council. If you were down at the Living Futures Conference yesterday, you may have heard Jason McClellan, yes, talk about his relationship with Dennis and how they, kind of brought that movement forward. So this is a building that's it achieved that lower EUI, so it has the ability to operate efficiently enough that it can actually be powered by the energy that can be captured within the PV canopy that sits above the building. You see another building down the street with the Edith Green one, the Wyatt project, which is also employing a PV canopy. It's way too big to have it supply all the energy. The building's way too big for the canopy size of that building. But yeah, I think that's something we're going to see as a wave of the future is roofing systems will be augmented with these canopy systems to capture the energy. This originally had a flap that came down on this side of the project that was a vertical element for the canopy, but then, like any project, cost constraints came to bear, and that was a very expensive element to basically cantilever a PV canopy off the side of the building sitting at a vertical angle. It was oriented well to the sun, but it just was a cost factor, so we reduced it back to just a canopy here. I know I'm kind of going all over the place, but if there's questions that you're having as I'm going along, please just jump out there. Interesting thing here is Seattle, many codes are very limiting that this project is breaking a lot of rules. So basically there's a special exemption that the city of Seattle has kind of created for these buildings that are attempting net zero to allow them to break some zoning rules. One of the zoning rules is our canopy sits over the top of the sidewalk. You think that's great, but it's actually in violation of the zoning code. But we all walk around here when it's raining, and it's really nice to have some cover when it's raining. But it's actually breaking the law. So that's one of the things. The other thing in this building that this building has a rainwater and a gray water system, and it also the waste in the building, it runs off a composting system. I'll show you. So these are some shots. This is actually a shot where that vertical piece was still there in the design. It was commonly referred to as the mud flap. The building has a extremely high performance exterior envelope. There's a German system, SCHUCO, I think is the name. And what they've done is they've worked with local manufacturers in the Northwest to actually license the local manufacturers in the States to produce the German SCHUCO system here. So it'll be a locally sourced but very efficient system for the skin of the building. And so one of the things that and you can see here is that all the windows operate, and they operate where you push them basically out from the building. You get tremendous opening areas. And when you bring them back and close them, you get a really good seal. So the building stays, from an infiltration standpoint, stays very tight when you want it to be tight, and it's very open when you want it to be open. This building has geothermal closed loop, just like the port building. It has radiant floors instead of radiant ceiling panels. I'll go on. This was an interesting piece that was done as far as the sizing of the canopy, and it gives you an idea of scale. This is a normal CBEX, normal EUI energy use for a building of this size, and you can see physically how large the canopy would have to be on top of the window or on top of the building if it were not a ultra low energy building. And then as you go through here, here's Seattle code, here's a LEED Platinum, and then here's the actual canopy size that we have with the enhanced EUI of the building. So that kind of gives you an idea of what really needs to be done in the buildings to bring this factor of producing your energy in scale. It was not a good site for wind, so wind was considered, but wind, the wind roses in the area and the average sustained speeds weren't really appropriate. You see, like on the 12 West building over in the west end over by Burnside, that there's those vertical turbines on that building. That's more of a demonstration, and it's kind of important because it's important to know that you can put wind generators on a building. Structural engineers go absolutely nuts when you put a wind generator on the building, to just be brutally honest, because it transfers vibration into the structure, and they want to start stiffening the entire building when you start, and so that causes a lot of cost premiums to go into the structural system of the building and stiffen it. But that's an interesting story about that project, but I won't get into that one. This was an idea of what that energy, this was a chart that shows those energy reductions. And the interesting part is that you see these large pieces that, like this piece right here represents the plug load, and it's getting smaller in the controlled factor, and it's getting even smaller here. But you see the heating and cooling energy, which are these two here, I think. Yes, those two. Basically, by the time you get here, they're gone. Between the night flush of the building, the geothermal system with the in-slab radiant, and the high-performance exterior of the building, lighting. Basically, the building is designed to have the lights off the entire day. And the only time the lights come on are at night when the sun goes down through daylighting control. There's interior shading controls like the port building. So you can kind of see this concept where these ideas are being formed, and they're being tried on a project, and then they're being implemented on other projects. And a lot of the architects we're working with and the design teams that we're working within kind of use that evolutionary process where we go try an element on a building, it tests well, we put it into this building. At the same time, you're using another element, it tests well, you put it into. And so this building is a perfect example of that culmination of many of those early concepts that then get transferred into a building. But I mean, the important part here to know is kind of the next movement in energy for us in a built environment is we've basically solved the heating and cooling. We can, maybe not from a budget standpoint, but from a materials and systems standpoint, we can solve the building heating and cooling. What we can't solve is the plug loads, this stuff. And so we're working very hard to try and actually be IT pioneers now to find alternate ways to bring the computing systems everybody needs into a building and do it in a way where we can start reducing that piece of the pie. Because when you get down here, that's the largest piece of the pie is what's in your plug loads out here. And over 25% of it is just related to the computer systems. So this is an example of a net zero energy building. The lights we brought way down. Space heating and cooling are basically down to nothing, 3 and 2%. You've got ventilation pumping systems that are supporting those alternate energy systems. But over here, this is the huge frontier now that you're down at that level. So it's very interesting to now start talking about elevators and equipment, getting into owners' equipment and making sure that we're using equipment that actually has like power-saving features. Drinking fountains. Drinking fountains, the little compressor doesn't have a time clock on it. You can't find one on the market now where you can get the compressor to turn off at night. There's things that we're trying to advocate and push for to kind of wring out these last pieces. But the energy from the computing systems are very impacted. A question?
Yeah. Virtually all the waste that you show on the flood waste there are the computer stuff and the printers and all these things that are all solid state devices that run off of low voltage DC. Had you looked at the ramifications of using low voltage DC?
DC networks?
And particularly to recover energy from your alternate sources like solar, which produce, because it's so much more efficient.
We are looking at that because, yeah, you're right. In a PV environment, you're taking in DC energy, converting it to AC, putting it in the building, and then taking your converters and converting it back to DC again. So DC buses are actually being installed and designed for buildings now, and that's one of those exploratory pieces that I was talking about that's actually being done now.
What are the limiting factors at this point in time?
Voltage drop.
Pardon?
Distance and voltage drop.
IR drop. Yeah. Okay.
It's difficult to, it's not like AC where you're more lenient that way. It's a little more challenging.
What about code issues? Is that a big thing now? Or?
No, not really. There's no code barriers in that environment. It all works within NEC code. So, there's no issues we're running up against that. It's just that your conductors are larger with the DC bus, and your voltage drop limitations mean that your line lengths have to be controlled. This is an example of this building's energy production and deficit surplus through the year as far as what we're expecting the building to perform like. This building's in construction. It's about 3 months away from completion. I think the skin of the building is going on right now. I was up there a few weeks ago. They were getting ready to put the skin on. This was an interesting study that we did. We looked and we said, well, why do, since we've done such a great job with the skin, we've done a great job with the lighting, we've actually written plug load limitations into the lease constraints for the building. Why do we even have to provide heating and cooling? Why can't we just operate it passively? So we looked at that and we used some bulk airflow modeling to look at what the hours would be without cooling on the second floor, fourth floor, and then with just sourcing the cooling through the radiant slab that what's already there from a heating standpoint for the building. So it's interesting to show that in this project, not a lot of expense, we were able to really knock out so many of those hours where maybe comfort would be at question, which is the mid 80s, mid low 80s. There were some hours here, and when we just circuited that to those radiant floor zones. What it means to me is pay attention for what's in the building. If it can be easily integrated and cross-connected, you can have tremendous benefits for the occupant. And part of this process is transforming our occupants. We're all occupants of a building. We're smart because we're engineers and we know, what all this means, and we know the difference between the different types of heat transfer, and we understand how our body works and how our body sees radiantly walls and windows and how we live in this mixed air environment. But the other people that are the 99% that aren't out there living in these buildings, they don't have that vision yet. They don't know that. We have to give them. I'm constantly training even the architects who should know what this means. Examples of sitting next to a cold window, that's radiant cooling, or outside at a little cafe that has a little propane heater, that's radiant heating. Getting them to realize what their bodies do as far as temperature with, on a windy day, wind chill across your skin, things like that. So there's a long ways to go for people to we can make the buildings, but we also have to educate the building occupants to live in the buildings and understand where their comfort's coming from and what, look at a temperature sensor on the wall. It may say 82 degrees, and I'm sitting there, it's like, but I'm comfortable. But maybe I shouldn't be because I see that temperature sensor says 82. Psychologically, you start thinking, I should be warm, and then all of a sudden, I'm warm, I'm sweating, I'm warm now. And so many times we fight that with our building occupants, just not having that knowledge. So actually, one of the things we're doing is we're kind of doing training seminars for the building occupants. We're going in and talking to them, giving them presentations, not as technical as this, but I mean more orientation, building orientation. We're training the people who are living in the building, and that's important to not lose track of. This is the water side of this building. It has quite a few systems, and again, code barriers. Right now we have a potable water system that actually takes rainwater and turns it into potable water with filtration and UV, but it's not code legal yet. City of Seattle won't let us run it. They don't have a approved process for that. So we're actually building it, and we're waiting for the advocacy that's happening right now to get these systems approved. We have a rainwater cistern that's taking rainwater from the roof. Part of it is being treated then for potable water, but for right now, we're going to be switching it over to the gray water system. The gray water system takes the fixtures in the building that are appropriately sourcing gray water and filters and treats that water and sends it back to the system to be flushed or to be reused in those systems, and also sending it out for irrigation. But this is an example of working with regulators and pushing the building industry forward. These processes are very well known. We just have to get everybody comfortable that it's safe and that it's reliable and that it will produce produce what we need. This building has a unique foam flush toilet system where the waste actually goes for composting. And there's a picture of the fixture. It doesn't look much different than a normal fixture. It's actually quite commonly used on like high-end yachts where flush water is kind of at a premium. So interesting. Again, borrowing the technology. I was talking about borrowing from education to medical or from high-tech to medical. This is, taking what was on a yacht and using it in a building in a way that gets the result that we want. This is what I was talking about earlier with a study of plug loads, and you were talking about. So this is actually our office. So we took our office, started in 2007, and said, what do we have? We know this plug load crunch is coming, so we started here with our dual displays. All of our people using AutoCAD and Revit needed big, powerful machines to run these high graphics programs. We morphed that with efficient power supplies to get this wattage down. We used more efficient monitors at this point in 2009 that were commercially available. And all this stuff was done for the same budget. Year after year after year, we had one replacement cost for these computers. And as they cycled, we had one budget. So then beyond that, we were able to get the LCD screens in, get that wattage down, using laptops as the source instead of conventional CPUs. And then this is the next piece we've worked on. We've gone to, I don't know if you've heard of like server virtualization. This is desktop virtualization. So we have actually taken the laptop and the CPU away from the desk. And we have this thing called there's multiple versions of it, but this is called a zero client device because it does not hold an operating system. All it does is communicate keyboard, mouse, video with a network. And then back at the network level, we have two servers that run, right now they're running 40 desktops. They're capable of running 100 desktops. So the average wattage per desktop is less than 5 watts per desktop that we're serving. And we're serving AutoCAD through this system to people to use out at their desktop. And the total is 42 watts. And if you remember, we started back here in 2007 at 250. So we've gone from 250 now down to 42. And the latest thing, we just got a monitor in our office now. These are two 22-inch monitors. Now you can get single 27-inch monitors that give you the same area viewable screen as the 22s, and it does it with one monitor. So we're able to go from the 28 watts here down to, I think it's around 15 watts total for the one monitor. So we're really pushing this down, and we buy the little kilowatt power strips, and we've done an actual full M&V system on our floor to look at HVAC loads, lighting loads, plug loads separately. So as we make these changes and sweep them out through the office, we can actually see the whole floor that this is on come down and its usage, and we have that monitored over like a 3-year period now to show, and we show that to our owners and then advocate, okay, you're going to be in a net zero building, you can live in this environment because here's a system that you can create that's under budget. So that's kind of the awkwardly, I guess that's kind of the end of the story that I have for you today, but it's a continuing story. Questions, comments? Yes. Okay, go ahead.
On just the very last slide, those little things, those are getting down to the power levels. Are those available on Power over Ethernet yet? That fits within
yes.
the 20.
Yes. The other thing is good that you brought that up. The latest product that we've seen is there's this device is built into the screen, and it's Power over Ethernet. And so you're doing everything that's here and here for like 17 watts. And it's one plug. And you can do your phone, and with the Power over Ethernet, you can also do a soft phone, and so you get rid of your desk phone, and your soft phone is connected to a Bluetooth headset, and you're actually answering your phone and talking on your phone on that soft phone display, because all the voice over IP phone systems now are all, network based.
What about power services, emergency services like emergency exit lighting and stuff like that? Does that fit in that environment yet, or is it still?
Well, one of the things that's happened in the lighting world for emergency egress lighting is there's been allowance now to put occupancy sensors in stairwells on occupied floors, so that in unoccupied periods the building goes black. It's legal now to take them and go black. Or if you have applications where you have natural light and you have high enough lighting level, you can put a photocell control, like in stairwells. I've got a project. I did the old Myron Frank's building conversion down here, which turned into the Nines Hotel, and all the stairwells on that building are on the outside wall, so they actually have glazing. So we've just turned the lights off with photocells during the day, and then at night they're just on occupancy sensors, and if somebody comes into a stairwell, they basically light up as you walk down, and they turn off behind you.
So you can see from the outside when people
You can see it, not that fast, but I think there are like 10-minute overrides or something like that. But it's becoming that acceptable to do that. Another question?
I have a couple questions. First is like kind of your closed and open loop experience on the thermal, and the issues around the capital cost and the operating and maintenance. Because I know this building has had some issues because it's on an aquifer with the water quality.
Yeah, a lot of sand.
Yeah, and so it's this open loop issue on an aquifer. You have these closed loop systems that are very expensive to put into all the wells, the individual wells. So in your experience, what are you finding in the comparison of those two systems, the performance and the cost? It's a very small sample set, but there's a lot of buildings in downtown that run on closed loop or open loop systems.
Yeah, I mean, you're exactly right. The open loops are much more cost effective. They do come with problems. I still remember this building when it was being commissioned. We were bringing sandbags to our office once a week because that was the filters. The filters came out looking like 10-pound sandbags. So we bring back the office and say, hey, look what we got from the job site today. Sandbag, So it's, but they are difficult. And one of the factors that I think about when I think about open loop is there's a responsibility for the aquifer and not adversely affecting the aquifer from a temperature standpoint. And DEQ has put a lot of well regulations in effect in the last few years to basically you have to license every well now, whether it's a dry well or a water well. So I think the open loop systems are going to become less prevalent because of the regulation, although they are still less expensive from an operational standpoint. 'Cause you still have the same effect. You still have, tremendous source of water at 55 degrees that you can extract heat from or reject heat to. The closed loop systems, I think, are going in the other direction as we're seeing more well drillers that it originally started as water well drillers that were used to just drilling one well and had frankly, very old style equipment. Now we're seeing more high-speed rigs with vibratory bits that actually can put in more of the closed wells on a faster turnaround and less cost. So I think we're going to see the closed loop well system come down in cost and the open loop systems rise up mainly from a regulatory standpoint. And there's concern if you start tapping an aquifer too much, you're either going to deplete it or you're going to temperature degrade it. And then it's tremendous the right now in the environment, the cost of the studies that have to go in for open well systems. That's another, it's a soft cost up front for studies, but it can be very large capital investment just to get the due diligence legal studies done. But so I think they're kind of starting to normalize a little bit. The system out at the port was very expensive. That well system was $1.5 million for the well system. But the other thing that's happening is that we're also getting some integration. I talked about integrated design. A project in Seattle we worked with had auger-driven piles, which they basically take a large drill bit, drill the hole in the ground, and then they put a reinforced rebar cage, and then they fill it with concrete. Well, we started strapping our geothermal tubes to that cage and dropped those in the ground. And that was really inexpensive because all we had to do was pay a crew to go out there and strap the pipe on and then connect it at the wellhead or at the piling. So as we get more integration between structure pilings and these wells, then there's a sharing of costs there that really will reduce the closed loop systems.
The other question I had was with regard to the final wide building down there. That huge shape structure, what do you think the impact is going to be on the heat rejection equipment that's on top of that building?
You mean as far as not having clear air above or
blocking radiation?
It's an interesting dynamic. I know that they're also using that canopy for rainwater collection and a rainwater harvesting system at the same time. So it's dual purposing. But I don't know on that one. We're doing the electrical side of that project. We're not doing the mechanical side of that project. But I was the peer review engineer that looked over the interior radiant designs because they're doing a radiant DOAS in that building for conversion. But I know there were a lot of studies done, but I don't know the answer to that question. Question?
What is the COP equivalent, if it's appropriate to use this term for the geothermal systems that you're describing, both the open loop and closed loop?
With out at I can answer that for the port. The port answer is about 3, roughly 3, and it's not as high as it could be because typically those rotary screw compressors are more of a high pressure machine, and it has a not as good of performance factor. But in the ability to produce heating energy at a COP of 3 as compared to a high efficiency gas condensing boiler at a COP of 0.92, there's a tremendous benefit of operating in that environment, with even a low COP.
But conventional flare couple heat exchangers as opposed to the ground couple heat exchangers, dual use for heating and cooling split systems these days have got a COP of about 3. And it's a sort of environment that have important. You don't have the lock-in effect of putting all that sunken infrastructure to use the building. And the COP of these systems are going up all the time.
True. If I understand your question correctly, though, you're just you're advocating for the reason behind putting in the geothermal fields?
Well, so just to get an idea of what the COP actually is and whether
Oh.
this has such a big performance advantage over the air-coupled systems, which are standard off-the-shelf.
Oh, okay.
And
Air coupled,
in 5
okay.
or 10 years' time, their efficiency goes up to replace them, as compared to the ground coupled, which you lock in for generation.
That's true. That's true. On the air side economy or the air side heat pumps, there is a lot of advancement also being made on the air side to run at lower ambient temperatures, which is helping that cost factor, because traditionally when we designed air side heat pumps, even in a Portland environment, we would have backup heating source. So from a cost standpoint, we'd have to still pay for some type of a fuel-fired system that would provide that backup heating when the air side system reached that drop-off temperature, which typically around 40 degrees. Yeah. So, but now with the advent of the lower operating condition air side heat pumps, you're exactly right that there's large devices that are just the air-cooled condenser heat pump that are producing like domestic water at high COPs. And that's a good point. I mean, there's not a lot of operational maintenance difference between those two either.
We probably only have one more question. If not,
Okay? Thank you.
What do you call, what was the naming term you use for these things?
That's a zero client device, and the system is called Virtual Desktop or VDI. VMware, if you've heard of like there's a software